Hey everyone, welcome to Unit 1, Lesson 1, Limit Notation and Evaluating Limits. This is the first video in our AP Calculus series, and we're going to be looking at what exactly a limit is, how we can evaluate it, and some different strategies and different representations of limits. If you're looking through the curriculum and wondering what outcomes we're hitting, we're going to be hitting these ones specifically from Unit 1, and in summary, these are the big outcomes that we're going to be touching upon in this lesson. So, first things first is to address this new notation that we're looking at here. So we have the limit of f of x as x approaches a is equal to L. That's how we say this out loud. So let's break this down. So LIM is just short for limit, okay? And what it's saying is the limit. It's asking us what's happening at f of x when x gets really close to some a value. Okay, so these are the three big parts on the left-hand side. So f of x is just like normal, can be any function that we would represent with f of x. So for instance, we could have f of x is equal to x squared. In that case, it's entirely appropriate for me to rewrite this as the limit of x squared as x approaches. And a here is just some number, okay? So I'm going to pick, for instance, 3. So if this is my work through of an example here, so the limit of x squared as x approaches 3 is equal to, and L is just a stand-in again for whatever the output is at that x value, provided that the left and right hand limits both evaluate to the same number. And I'm going to get into more details what that means, but in essence, if we just think about our x squared graph here, and you're imagining like, okay, you got a basic parabola, all this is really asking is, hey, what's happening at f of x when x is equal to 3. And so hopefully you guys can think about that for a second and realize, okay, when x is equal to 3, well, 3 squared is going to give me an output of 9. So the limit of x squared as x approaches 3 is 9. Now, some important things to note here is when we're talking about limits, I know I'm talking about plugging 3 in and evaluating it and all that, but a limit is actually us going infinitesimally close to that point, but never actually reaching it. But because we're going so infinitely close to it, we can treat it as if we were at that point for algebraic reasons. But it's also important for us to be cognizant of that fact that we're not actually going all the way to 3 from either the left or the right-hand side. When we're talking about notation, when you're showing your work, you keep this limit notation in until you get a number. It doesn't have to be a simplified number, but as long as what you have evaluates to a number, you then remove the limit. So for instance, if I was to show that work, what I just showed there, so if I had the limit, let me just treat this like a normal question here. So the limit of x approaches 3 of f of x is equal to the limit of x approaches 3 of x squared. So because I actually haven't done any substitution yet, I still keep that limit in. However, the moment I put the 3 in and write 3 squared, that's when I take the limit out. Now, I should simplify this for posterity's sake here. So the limit of f of x as x approaches 3 is equal to the limit of x squared as x approaches 3 is equal to 3 squared is equal to 9. It's important to keep that limit notation in until you actually do any substitution. Okay, so this is essentially saying what I was just mentioning on the previous page. And graphically, if you've got the the graph in front of you, all you need to do is actually look to see what's happening. So here we've got f of x, and we're being asked to find what's the limit as x approaches 4. And so I can look at the graph here and say, okay, as x approaches 4, it's getting closer and closer to 2. It's getting closer and closer to 2 from the left and the right-hand side. So the limit then is 2. If the left and right hand sides aren't the same, so for instance, if it was going, towards positive infinity here and going towards negative infinity down there, then the limit we would write is dne. It does not exist. You can write it out if you want, but dne is an accepted shorthand, and we'll get into more detail on that in a few slides. So if we're evaluating a limit graphically, it's as simple as looking at the graph and seeing what it outputs to, provided left and right hand limits are the same. If we're talking about algebraically, first off, try substituting the value in, like I did on the first slide there. And if you get a number, awesome, you can move on to the next question. If you're getting an error, like dividing by 0, then you want to try factoring and eliminating common factors. If you are still getting an error, specifically an error of 0 over 0 or infinity over infinity, we're going to employ something called L'Hopital's rule, which we'll learn a little bit later in a few lessons. But by the way, dividing by 0 is perfectly fine. It just means that you must be tending towards positive or negative infinity in some cases, depending on the case. And yeah, so dividing by 0 is fine. It's when you have 0 over 0 that is an error, is indeterminate. We're not sure what's going on there. So let's look at this right here. So we're going to evaluate both of these algebraically. And now ideally I would kind of be working horizontally here. And it's important for me to note that if I was working horizontally, I'd be including an equal sign and writing everything out. I'm going to be working vertically here. So I'm just going to substitute a value in. And when I substitute that value in, I don't need to include the limit. So I'm just going to go 2 squared minus 81 all over 2 times 2 squared minus 7 times 2 minus 9. And that's the limit at this point. Now I can see right away that this is not going to give me any sort of error, like I'm going to get some number over some number. In AP, you can actually leave the answer just like this. You do not need to simplify anything as long as your substituted value, once you substitute a value in and the expression will evaluate to some number, you can move on. Now, depending on the context, it is nice to simplify, or if it's a multiple choice, then of course you're gonna have to simplify to see, if it lines, what answer it lines up with. But again, this is actually fine to leave as is in AP, but we're gonna simplify here. So this is just gonna be 4 minus 81 all over 8 minus 14 minus 9. And that would, by the way, would have an equal sign here. And we always want to have stuff on either side of our equal sign. So 4 minus 81 is negative 77 all over 8 minus 14 is negative 6. And negative 6 minus 9 is going to be negative 15. And so 77 over 15 can't be simplified or anything. So that's nice and easy. We can just leave it as is, or you can simplify it, I guess, to be 77 over 15. So let's try this one out. So here I can tell right away, as soon as I substitute a 0 in, I'm going to have zeros everywhere, and I'll end up with getting 0 over 0. So I don't want to do that. I'm going to try factoring then. So I can see in the numerator here, I can definitely factor out an x. And I'll be left with x squared minus 16 all over, and then I'll factor out a 3x in the denominator. So I'll get 3x minus 4. And I can see again that I can keep factoring my numerator. So I'm going to have x minus 4, x plus 4, all over 3x, x minus 4. And so when I'm looking at things I can cross off, I can definitely cross off my x minus 4s. I can cross off my x's. And I'm going to be left with, in terms of an expression, I'm going to get my pen back here. I'm going to be left with x plus 4 all over 3. So I'm going to be evaluating the limit of this as x approaches 0. And then that's going to end up being 0 plus 4 all over 3, or 4/3. Let's keep going. So left and right hand limits. So I've sort of alluded to this, but when we're talking about left and right hand limits, what that means is I'm going to be looking directly to the left of A and directly to the right of A. So for instance, if I have something that looks like this, and I'm looking, at 4, and this output, let's say, is 3, the left of A means that I'm going to be looking to see what happens as I approach it from the left, as I get really close to whatever that number is. And the right hand means I'm going to be approaching it from the right and seeing what the value is. Now, in this case, the left and right hand are the same, which means they're going to have the same output, which means the limit itself exists. However, that's not always true, especially when we talk about like piecewise functions, and you can have, we'll just use right here for this one. So for instance, if you have something like this, and you're talking about a function with a jump discontinuity here, that should be filled in. And so let's say we're approaching 1. And this is 2, and this is negative 1. My scale's not that great here, but so for instance, the limit of f of x as you approach it from the left-hand side, well, in this case, it's 2, if we're talking about 1. And as you approach 1 from the right-hand side, it would be equal to negative 1. Because as we're approaching from the right, we're looking to see that, hey, we're getting closer and closer to negative 1. Here from the left, we're getting closer and closer to 2. So our left and right hand limits are different here. So the actual limit itself does not exist. So if the left and right hand limits are the same, then the limit as x approaches a can be evaluated. And that's sort of what I was saying here. It's exactly what I was saying here as your limit has to be, in order for your limit to be, in order for you to evaluate your limit, you need to have an equal left hand and an equal right hand limit. And then interestingly enough, you can still have an undefined a at that location too, because you can have a situation like this where you've got like a removable discontinuity there. And so as you approach from the left-hand side, you're getting closer and closer to the same number. As you approach from the right-hand side, you're getting closer and closer to the same number. So this function here, its limit, the limit exists, but the actual f of a value, whatever a is right there, does not exist. So f of a does not exist, but the limit as x approaches a of f of x, there is some number there. It does exist. And that's just like an interesting quirk of dealing with limits. So let's read this and let's go through some stuff here. So the limit of f of x as x approaches 0 from the right-hand side. So as x approaches 0 from the right-hand side, I'm looking here. So it's going to be 0. The limit of f of x as x approaches 0 from the left-hand side. I'm going to be looking at this right here, approaching from the left-hand side. It's definitely going to be 0. The limit of f of x as x approaches 0 then, as long as these two are the same number, then I just copy and paste what that number is. If they were different, I would write dne. And finally, f of 0, does f of 0 exist? Well, that's nice and easy. I can just plug in 0 to my function here and say, okay, 0 squared over 0, does that exist? What's that output? And hopefully you can see that no, it does not. It is undefined at that point. So if I was actually drawing this by hand, I'd put a little hole right here. Desmos doesn't include holes unless we, plug them in ourselves. So I'm going to just put a little hole right there to indicate that 0 is undefined. Okay, let's look at this example here. So here I've got some piecewise function with a jump discontinuity, and so let's look and see what's going on. So the limit of f of x as x approaches 3. Before I do this one, I'm going to do my left and right hand limits first and see what they evaluate to. So the limit of f of x as x approaches 3 from the left-hand side. So I'm going to look at f of x as it approaches 3 from the left-hand side. I'm getting closer and closer. You can see here I'm going to go and approach 6. So this evaluates to 6. The limit of f of x as x approaches 3 from the right-hand side. So from the right-hand side, as I'm following along the function, I'm getting closer and closer to 10. Which means as x approaches 3 for f of x in general, because these are different, then this right here does not exist. There is no limit for f of x as x approaches 3 because the left and the right-hand limits are different. And finally, if we just look at what f of 3 is, well, f of 3 means I'm going to look and see where it's defined at 3. So that's a hole, means there's nothing there. That's a hole, there's nothing there. At f of 3, the output is actually 0. So here's a case where we have 4 different questions and we have 4 different answers to them, which is different than a situation like this where we have a lot of similarity. And for a continuous function, if you're just talking about a function that's continuous, all of these evaluate to the same thing if you're looking, if you're just picking some random point from that continuous function. So let's look at this one right here again. Lots of things that we can do to interpret this. And this is something that AP will often do, is they'll give a graph and ask very similar questions and get you to see what's going on. So the limit of f of x as x approaches -1. So as x approaches -1 from the from the left-hand side and from the right-hand side, it's actually approaching the same number, so it's equal to 2. Even though f of -1, and if you look at over here, there's a question of f of -1. F of -1 is undefined or does not exist, or undefined, however you want to say it. There is nothing there at f of -1, but the limit is there because the left and the right-hand sides are the same. Let's look and see what's happening as the limit of f of x as x approaches 2. As x approaches 2 from the left hand and from the right hand side, clearly those are 2 different numbers there. So this does not exist. There is no limit as x approaches 2. Oh, whoops. However, as x approaches 2 from the right hand side, if I look from the right hand side here, well, the limit is 2. As x approaches 2 from the left hand side, it's 0.5. And finally, f of 2, I look to see which of these is the filled in dot, and the filled in dot then would be at 0.5, because this is where it's defined. right there just means that it's like the point 2 comma 2 is not part of the function. The next point would be like 2.0 to infinity 1, which, we can't really evaluate, but the endpoint here is included. The endpoint there is not included. Okay, let's look at infinity here. So the limit of f of x as x approaches infinity. Now, when you get an oscillating graph like this is actually a tricksy question because you're oscillating with a minute from, you're basically going between 2 and 4, always along the sinusoidal graph here. So because as you approach infinity, there's no clear trend towards a specific number, it's DNE, it does not exist, okay? If it was trending, for instance, let's say this graph was like just an exponential graph and was always going up, then your limit of f of x as x approaches infinity would be infinity at that point. Or if it was, if it was a transformed exponential graph and it was flipped and it was kind of approaching 0 like this as x got towards infinity, then it would be limit as of f of x as x approaches infinity is equal to 0. So you've got to sort of pay attention and see what's happening. If it's tending towards some specific number, or if it's not tending towards some specific number, then the limit does not exist at infinity. So this is where I'll pause here. This is a link to just an AP activity. Please come find me if you have questions. You can contact me through Teams, through email, and if not, I'll see you in the next video.